In this video, I'll be going over what an axiomatic system is and how we define certain properties they have. We'll also be looking at how changing axioms gives us different types of geometries and what value they give us. If we remember from our first video, I talked about the main components in an axiomatic system: the terms, axioms, and propositions. It is important to note that we'll not be stating our basic terms like we did in the first video, and they're usually assumed to be a point, line, and intersection. Before we go into the main properties, we'll start off with two basic definitions: interpretations and models. Interpretations are just another way of giving meaning to undefined terms. These are most commonly shown through visuals of what the undefined look like and possible interactions they have with each other. Likewise, models are interpretations, but more specifically follow all of the axioms in a given system. We'll see what this looks like in our next example. We usually define systems with three terms: consistency, independence, and completeness. We'll first start off with consistency. For an axiomatic system to be consistent, we cannot have any logical contradictions with our given axioms. We can show consistency if a model can be made. But how do we do that? Let's look at the example system. When we're making models, the easiest way is to start off by going down the list and trying to fit each axiom. With our first axiom, we can draw 3 points. Note, our axioms say nothing about the positions of our points, so these can be anywhere we would like them. Now following axiom 3, each pair of points are on one line, so let's draw a line between each pair. Going back to axiom 2, we see that not all of our points are on the same line, so this axiom is satisfied. With our model, we satisfy all 3 of our axioms, so that means our system is consistent. Our next term is independence. A statement is independent if we cannot prove it using other axioms. An axiomatic system is independent if all the axioms are independent. To show the independence of our axioms, we can do this by making a model with each statement negated. I'll briefly cover over what it means to negate, but it essentially means to take the opposite of what is being said. There will be 2 types of statements we will be negating: universal and existential statements. Universal statements apply to all cases, hence its name. To negate universals, we say that there exists something that does not follow the original statement. Let's look at the statement, "If it rains, then all roads get wet." This is a universal because it is talking about every road. Now the negation of the statement would be, "If it rains, then there exists a road that does not get wet." Now we go to existential statements, which tell us that there exists an object that follows specific conditions. To negate existential, we say that for all cases, or cases that are not covered, do not follow the original statement. Let's take the statement, "If a car breaks down, then there exists a mechanic who can fix it." This would be existential because we say that there is at least one person, not all, who can fix it. The negation of the statement would be, "If a car breaks down, then all mechanics cannot fix it." The reason why we use the negation is because if our system is independent, one statement should not affect the truth of another. Just looking at our 2 example statements, these would be considered independent because the validity of one statement is not dependent on the other. Whether the rain gets the road wet or not does not impact whether or not there exists a mechanic who can fix a broken down car. This also applies vice versa. Now let's apply this to find independence for our previous axiomatic example. As a reminder, to show independence, all we need to do is create a model for each negated axiom. Our first one will be with axiom 1 negated, the other 2 as normal. The negation turns it into, for all points, there is less than 3 points. Since we can have less than 3 points, let's just choose 0 points. Well, since we don't have any points, we don't have to worry about the application of axiom 2 or 3, since those are conditional on having a line. Even though it looks like we have nothing, this is a valid model for this negated statement. Now let's negate the second statement. Negating it turns into, there exist points that are on the same line. With our first and second axiom, we know that there has to exist 3 points, and all of them have to be on the same line. So let's just create a line that has all 3 points. Going to axiom 3, each pair of points are on the same line, so that is satisfied, giving us our valid model. Now let's negate the last statement. Negating this turns into, there exists a pair of points that are on not exactly one line. Let's just start off with the first axiom and draw 3 points. Our negated axiom tells us that pairs of points cannot be on only one line. If we had a line going from one point to another, to satisfy this axiom, we can just make another line that connects both of these pairs. We can do that for every other pair. You may also realize that we could have 3, 4, or even 0 lines connecting a pair of points. Those would also work because it satisfies the negated condition as well. With that, we're able to draw a model for each negated axiom, thus proving that our axiomatic system is independent. The last way we define axiomatic systems is with completeness. An axiomatic system is complete if any statement using terms of the system can be proven or disproven. To prove that an axiomatic system is complete is very difficult, so instead we'll be proving that a system is incomplete. We can do this by finding at least two non-isomorphic models. Isomorphism just means when two things have the same mapping. If we go to the first model we made, an isomorphic model could also look like this. Even though these diagrams do not visually look the same, they have the same properties where there's only 3 points and lines, such that each pair of points have a line between each other, and there's only 2 points on each line. Going back to the meaning of our primitives, we can also make these look however we would like them to, as long as they have the same properties. For example, let's assume instead of having points, we chose to define these with mugs, and instead of having lines, we chose to define these as tables. Even though we are using two completely different looking terms, the mapping is still the same. Each point or mug is on two different lines or tables, and each line or table has only 2 points or mugs on them. Therefore, these two diagrams would also be considered isomorphic. Now, let's go back to our example system and show the system's incompleteness. All we need to do is show a model that has a different mapping. Our first axiom says that we need to have at least 3 points, so let's make another that has 4 instead. Going with the third axiom, we'll make a line between each pair of distinct points. Our original model and our second model have different mappings, and are therefore non-isomorphic because there's a different number of lines and points. But I do want you to realize that isomorphism is not just limited to the number of points or lines, but we can also differ depending on the number of intersections or where those occur. Next, I'll be introducing incidence geometry. Incidence geometry is a more notable type of geometry, which you'll see very commonly in axiomatic geometry because of how basic it is. As an exercise, try to see if you can determine if it's complete, independent, or consistent. Hence the name incidence. Incidence geometry is mainly used to show the intersection between objects and relationships they may have. One question that may arise is, why do we need so many types of geometries, and what is their use? These geometries let us model different scenarios and let us analyze them depending on what types of rules we want to put in place. Just like how we saw in our isomorphic demonstration between the model with points in a line and to the model with mugs and tables, if for some reason we wanted to know the interactions between mugs and tables and had rules that were identical to geometry that we created it from, we could use this geometry to formulate theorems and rules. As a closure, axiomatic geometry is very functional with the flexibility in axioms and the way we are able to define them. In the description, there are some related practice problems with the solutions if you wanted to get a better understanding of the topic. Either way, thank you for watching and hope to see you next time.